Welcome to Lecture 6, Section 1.3, Applications of Systems of Linear Equations. We are using the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. This is Dr. Gilbert, Eyabi. The first example in this section is a procedure called the polynomial curve fitting. Suppose x1, y1, x2, y2, xn, yn are endpoints in the xy plane that represent a collection of data. And your task is to find a polynomial function of degree n minus 1 whose graph passes through the specified points. I.e., you want to find a polynomial of the form p of x equals a0 plus a1x plus a2x squared plus an minus 1 x to the n minus 1. This procedure is what we call polynomial curve fitting. Now I want you to observe something. There are endpoints x1, y1, x2, y2, xn, yn, and the polynomial function we are interested in has degree n minus 1. In other words, the last term would be a n minus 1 x to the n minus 1. Always remember this. N points, polynomial function, degree n minus 1. Now, if all x coordinates of the points are distinct, then there is precisely one polynomial function of degree n minus 1 or less that fits the endpoint. So how do we proceed with this procedure called the polynomial curve fitting? To solve for the n coefficients of p of x, substitute each of the endpoints into the polynomial function and obtain n linear equations in n variables. The variables would be a0, a1, a2, right up to a n minus 1. Now you see here we have n variables and n points, but the polynomial has degree n minus 1. So if we substituted the first point into this linear equation, we would have a0 plus a1x1 plus a2x1 squared plus an minus 1 x1 to the n minus 1 equals the corresponding y1. We do that for all the endpoints. We end up with n linear equations and n unknowns. We set up our augmented matrix and use either the row echelon form REF or the reduced row echelon form RREF to solve the system. Okay, a quick and a simple example. Determine the polynomial function p of x equals a0 plus a1x plus a2x squared whose graph passes through the points 1, 4, 2, 0, 3, 12. Now recall that we may not necessarily give you this polynomial function as it is. A standard way to ask this question would simply be determine the polynomial function whose graph passes through the points 1, 4, 2, 0, 3, 12. It is understood that since there are 3 points, you should have a polynomial of degree 2. Okay, solution. Now, the x values are 1, 2, and 3, and their corresponding y values are 4, 0, and 12. So substitute x equals 1, 2, and 3 into the polynomial function p of x and equate the results to the respective y values. And that would give us equation 1, A0 plus A1 plus A2 equals 4. Equation 2, we perform the same operation. We have A0 plus 2A1 plus 4A2 equals 0. Equation 3, A0 plus 3A1 plus 9A2 equals 12. Now we simply get the augmented matrix and solve the system and arrive at the solution. A0 equals 24, A1 equals negative 28, and A2 equals 8. Substituting this back into our polynomial function, we end up with the required polynomial function, which is p of x equals 24 minus 28x plus 8x squared. And using your iPad, Math Studio, we can graph this function very easily. So that is our first example, polynomial curve fitting. Now there are several other examples we'll look at, and I want us to discuss a little on network analysis. And the basic assumption of network analysis or network flow is this. Number one, the total flow into the network equals the total flow out of the network. So it doesn't matter whether it's water that flows through a junction or flows into a network, or traffic that flows into a network, but the total flow into the network must equal the total flow out of the network. Number two, the total flow into a junction equals the total flow out of the junction. So we are looking at the entire network, and then we are also looking at a particular junction. The total flow into that junction must equal the total flow out of that junction. Whenever a negative flow appears in a network branch, then we view that as the direction being opposite to that shown on the model. Okay, now the second analysis would be electrical analysis, and an electrical network is another type of network where analysis is commonly applied. An analysis of such a system uses two properties of electrical networks known as Kirchhoff's laws. The first law states that all the current flowing into a junction must flow out of the junction. All the current flowing into a junction must flow out of it. Number two, the sum of the products I times R, where I is the current and R is the resistance around a closed path, is equal to the total voltage in the path. So these two laws are known as Kirchhoff's laws, and we would be using these two laws to solve several problems on electrical analysis. Now, some quick remarks before we start looking at some examples. In an electrical network, current is measured in amps, resistance in ohms, and product of current and resistance in volts. And the following two symbols, the first one represents a battery and the second one represents resistance. In the next lecture, lecture 7, we would look at two examples. The first example is an analysis of a network, and the second example would be an analysis of an electrical network. Thank you.